Okay, we should move on now. There's a nice segue into Ting-Yun Cheng, who's going to talk next on machine learning applications on galaxy morphological classification by using dark energy survey images.
Hi there, I'm Ting-Yun, and just call me Sunny. And I'm a PhD student in University of Nottingham, and my supervisor is Chris Constance and Arrogant. So I decided to change my title because just 2 days ago, I decided to add another part of the part 2. The part 2 that is talking about a new unsupervised machine learning technique I'm currently developing. So here I will just do the brief introduction later. And thanks for the Jim and Andrew's talk. So it kind of gave me a lot of background and I can save a lot of time later. So the part 1, I'll focus on the supervised machine learning, which is my first project in my PhD. That I compared several common methods, supervised machine learning methods, and using imaging data, and to compare with the convolutional neural network. And here we're working on dark energy survey. And here we got 2 main investigations of the papers I will show later. So this is all the 7 supervised machine learning we are going to talk about: the Canyon-Snapper, logistic regression, and logistic regression combined with a single-layer neural network, and support vector machine, and the same combined with a single-layer neural network, and the multiple layers perceptron neural network, and the convolutional neural network. So as you know, apart from convolutional neural network, there are most of them generally use a parameter input to do the galaxy morphological classification. Something like a surface brightness profile, magnitude, color, use this parameter to do the supervised learning. So there are not a comparison of them to using imaging data to compare with the performance of convolutional neural network. So that's why it cancels out my research for that. So we use dark energy survey year 1 gold data, and we matching with the visual classification of Galaxy Zoo project. And that gives us a total about 2,800 image galaxies. And because it is a little number, so we rotate image to do data augmentation. So after rotation and adding some Gaussian noise and rescaling, we got the raw image that as an input. And in this study, we also use a gradient image of the raw image, which we use the technique is this histogram of oriented gradients. Basically, you just calculate the gradient of the pixel value, and to get the image, and which can sharpen the edge and emphasize the shape of the object. And for convolutional neural network, we also have another input is combined raw image input and gradient image together, so we call it combination input. So the first investigation that we showed a comparison of different type of input data. So here is a ROC curve. So thanks for the first speaker, this already explained what is ROC curve. Then here is 7 different methods, and as you can see, the crayon color is raw image, and the orange is a gradient image. So as you can see, the gradient image input actually help the performance for most of methods, and apart from Canyon-Snapper. And the convolutional neural network here, when we use the combination input, it can significantly push it further, more accurate in here. Okay. So here is the comparison of the accuracy versus different methods and with different data sets and different input type of data. So it's very obviously that convolutional neural network is still the best method at the moment for supervised machine learning, which I'm not surprised. But this table here we showed in my paper that I showed the efficiency, the comparison of the efficiency of different methods. So you can see the Canyon-Snapper and the neural network. They can get actually not a bit, quite a good accuracy using very, very less time training. So just a few seconds. And especially for Canyon-Snapper, that surprisingly, they only use raw image input, then they can get this accuracy. which means you can also save the time to do the preprocessing. You don't need to use that time to generate gradient image. You can get this accuracy already. So in my paper, I suggest that, and I give an idea that k-nearest neighbor and the MLPC neural network actually are the good alternative option for convolutional network when you're using imaging data. So we use the maximum available number in my training set, and using a convolutional network and the combination input, we use the probability criterion 0.8 to get the accuracy of 0.987, which is very good in this type of classification. And uncertain type here, which means the predict probability is lower than 0.8, so we call it uncertain type, is about 4% in this case. So next, the next investigation here, I want to investigate the value in my convolutional network. So what is value? I define two types of value in my convolutional network. First one is it is misclassified when you compare with the visual classification of Galaxy Zoo. But actually, it got very high predict probability in our convolutional network. So that is one type of value, and the other type is uncertain type. So it turns out, actually, the first type, they are not really a misclassification in our CNN. They are actually mislabeled by Galaxy Zoo, which need to be updated because in dark energy survey data got a better resolution and a deeper depth than the Sloan data. So you can see these two images are the same galaxy. So you can see here in this data, it showed the significant spiral on structure, which didn't show in Sloan data. So that's why in our convolutional network, we classify it as a spiral because in test we see this structure. But in Galaxy Zoo, because Sloan data doesn't have it, so they classify it as elliptical. So we find a total about 2.5% galaxy in our sample, which is mislabeled by Galaxy Zoo. And we correct that and do the retrain. So it improved our accuracy to over 0.99, and it decreased very significantly decreased the uncertain type, the number of uncertain type. And uncertain type value this part, we realized that actually they are visual lenticular galaxies. So this is because in Galaxy Zoo project, they don't really have a class for lenticular galaxy. So actually, for lenticular galaxy, they classify them as like half spiral, half of them will be elliptical. So this confuses our CNN. Therefore, our CNN, we intend to predict them as a lower predict probability. And this, in our paper, we call it a rediscovery of lenticular galaxy, which we didn't expect when we did this study. Okay, so here is a little summary of the first part. So just briefly, like k-nearest neighbor and a neural network actually are good alternative option when you're using imaging data. And we reveal some mislabeled galaxy in Galaxy Zoo because that data is better than Sloan data in the resolution and the depth. And after correcting that, we push our methods to the accuracy of over 0.99 in galaxy morphological classification. So the part 2 is about the unsupervised machine learning. Here, I'm going to propose a new unsupervised machine learning technique for astronomy, which is different from what Jim just talked about. So it will be interesting to compare each other. Then here we use the simulated data from strong lensing challenge, which is also Andrew just mentioned, the strong lensing finding challenge. And we use the space, so which is the simulated data for Euclid. And they only got one band, which is a visual band. And here we are going to briefly introduce 3 main advantages of this technique. Okay, so we already know that convolutional network is very, very powerful supervised machine learning at the moment. And so we want to use, so the idea is very simple. I want to combine the convolutional neural network, the feature extraction part, with unsupervised machine learning. However, the convolutional neural network is, as we know, is supervised machine learning. So in unsupervised manner, we are going to introduce something called convolutional autoencoder. So this is the architecture of convolutional autoencoder. The white part is convolutional layers, and the red part is neural network. So you can see the left-hand side this bit is just basically like an architecture of convolutional neural network. And the center, the yellow in the middle, this center part is in the center. So left-hand side and the right-hand side need to be totally symmetric. Then the purpose of this convolutional autoencoder is we input image, then we want to output exactly the same image. So we're using this middle, the center of the central layer, this bit, is here we use 16 units in this neural network. So that means we use 16 features to describe this input image. And based on these 16 features, we can reproduce the image as output. So if our output is as close as input, that means these 16 features must do something good, right? Okay, then we combine these 16 features with unsupervised machine learning, then they can do the cluster just based on this feature that extract out. So here we talk about the first advantage of this new technique is that it's purely unsupervised machine learning, and it not only separates the features of lensing and non-lensing, it also can distinguish different type of lensing. For example, this group, it showed a strong significant Einstein ring, and this one is fainter Einstein ring, and here it shows the arc structure, and it's like multiple object. Oh, okay. So in unsupervised machine learning, when I started to do it, I discovered there's a question you need to clarify, that can we use pure unsupervised machine learning to do the classification compared with supervised machine learning? Which I would say is no, because the classification we know, like lensing, non-lensing, spiral, elliptical, actually they are all based on human judgment. So if you imagine that this technique is just a baby, he doesn't know what is lensing, what is spiral, what is elliptical. They just classify them as based on how they look like. So that is also the main point and the core idea of unsupervised machine learning. So if we do want to do the classification and compare to supervised machine learning results, we need to make human judgment get involved in a way. So the second advantage of this technique is if we do want to do some classification to do comparison, we only need to classify these 16 features instead of thousands, 10,000 images. Just classify them one by one. This is lensing, this is not, this is lensing, this is not. We just need to classify this 16 group. Okay, so I need to speed up a bit, sorry. So here we can, here just a method that I use to calculate that. So this is a probability of image belong to this group, and each group got a percentage of lensing in this group. So we can know that because we are doing unsupervised machine learning, so of course we won't know how much percentage in this group, how much percentage of lensing in this group. So it's unknown. So here I do a little trick that I look at the image, and if they got very strong features, lensing features, and more than half population in this group, I said that, oh, okay, this is lensing. So I set the possibility of it is 1. And if it doesn't really have any clue about lensing, and I set the probability of 0. And some condition that is a little bit difficult to tell, I set is 0.5. So use that, we can get some ROC curve to do the comparison. And here is using the percentage, which is true percentage lensing in the group. And here is using the little trick I just said, is assume a probability for that. You can see it shows quite consistent, so actually this little trick does can work. So we compare our result with the lensing finding challenge and discover that our result is better than human classification. And here is where we are. So we even better than some of the typical machine learning, supervised machine learning, and convolutional neural network. So here is a little summary for that. And my future work is, for the first part, we are currently building a catalog for Gaussian morphological classification for DES year 3 data. And in the second part, that this is a new technique. It's very new idea. It's easy, but it's quite new. So it still needs a lot of investigation to that. And color information need to be included in the future work. And this lensing actually is just my side project. My main project is also want to do the Gaussian morphology and want to push to know how the evolution of this galaxy morphology just by looking at this image. Yeah. So thank you, everybody.
So in the first half, we looked at all the different classifiers, and the CNNs performed the best. Did you check whether an ensemble with all the other classifiers might do just a little bit better still?
Pardon me?
Did you check whether an ensemble using all the classifiers would do a little better than the CNNs alone? Or are the CNNs better than everything else combined? Or as good?
Well, so I didn't say the detail about that. So I have exactly the same training set for every method. Then the same testing set for every method. So it just, in my paper, I showed more that the comparison of raw curve, accuracy, everything, that it shows, well, convolutional network still better. But if you consider about efficiency, even you use GPU, it takes about an hour to finish it. And without GPU, it will take at least 12 hours. So that's why we do the comparison of efficiency. Then you will realize Kenyan is stable and neural network seems not too bad. Yeah.
So thank you very much for both the parts of the talk.
So these, the autoencoders that you're using, so I think of those as something like a more advanced version of traditional PCA, right, in terms of feature reduction, compressing your information into a number of features. So in traditional PCAs, you have a way of systematically selecting how many features you're going to be using. How do you do this with autoencoders, or is there a way that you go about deciding how many features your final layer before you start decoding?
In PCA bit, I did do some tests before, but because we use image data, so basically you just, this image is 100 or 1 times 101, so it's basically I got over 10,000 features you need to extract. And in PCA, it's actually not as good as convolutional architecture, right?
I understand that. I mean, like when you're autoencoder, you got down to 16 features. So when PCA, there's ways of looking at how much variance is in each feature.
Oh, you mean using PCA to this 16?
No, I mean, how did you decide that 16 was a correct feature number
Oh.
for the autoencoder?
I see. So in this part, actually we did a test, just do the easy plot, the accuracy of the final result and versus the number of features. So it's try and error. So at the moment, 16 things work well, but I also tried use a log image. Then it seems like 20 got a better result, which it can push our AUC to about 0.86. Yeah, which is much better than the human eyes.
I had a question about the gradient images. Like, what's the balance and efficiency between including the combined data set versus just making a deeper network that can pull out the gradients?
Actually, that's a very good question. I never really done this test before. Yeah, but I'm not quite sure. If you put it deeper and deeper, then you would consume more computing time. So, but if you do the gradient image, basically you just done once pre-processing, then that's done. Yeah. And I'm not really sure about if you use a deeper layer it can truly get the information of brilliant image it can provide or not. That is another problem you need to think.
Thank you. This is a really great talk.